The last examples that we're going to look at for this section on the sum and difference of trig function angles is tangent. So the tangent formulas look quite a bit different than the formulas that we looked at for sine and cosine. Taking a look at the first one, when we are looking at the tangent of two angles being added together, or good old alpha and beta, this is equal to the tangent of alpha plus the tangent of beta, so in the numerator. And in the denominator, it's 1 minus the tangent of alpha times the tangent of beta. So for plus, we have a plus in the numerator and then a subtraction in the denominator. When we're looking at the tangent of the difference of two angles, we have the subtraction here. And our formula is, again, the tangent of alpha and the tangent of beta in the numerator, but this time there is a subtraction between the two, so the subtractions match. And in the denominator, it's 1 plus the tangent of alpha times the tangent of beta. So the formulas for tangents. So now, taking a look at a reason why we would consider something like that, if we wanted to know the tangent of 7 pi over 12, again in this world where a calamity has occurred and there are no calculators or software to do this, we wouldn't be able to determine what the tangent of this angle is. So what we have to think about, is there a way we can break down 7 pi over 12 into two angles that would give us something that we could evaluate? So if we think of 7 pi over 12, we could use 4 pi over 12 and 3 pi over 12. So we would look at the tangent of 4 pi over 12 plus 3 pi over 12, and that's equivalent to the tangent of 7 pi over 12. And why would we do this? You say, well, in this form, it's not as readily seen the benefit of breaking it up like that. If we simplify these fractions, 4 pi over 12 is the same as pi over 3, and 3 pi over 12 is the same as pi over 4. And now pi over 3 and pi over 4, these are angles that we recognize and we can evaluate the tangent for. So let's call pi over 3 alpha, just because I feel like getting its first, but as usual, this could be our alpha and this is our beta, but I'm going to call this alpha. So this is going to be our alpha and this is going to be our beta here. So our alpha and our beta angles. And now the formula says that the tangent of alpha plus beta is equal to the tangent of alpha plus the tangent of beta, and this is all over 1 minus the tangent of alpha times the tangent of our beta. We're going to need to know the tangent of both of these angles. So coming back over here, let's do it here. The tangent of pi over 3 is equal to square root 3. This is our alpha. And the tangent of pi over 4, this is 1. And this is what we're going to use for our beta. So we've identified the pieces. Similar to what we did for sine and cosine, we need to get the exact trig values for our angles. Now we can go and we can substitute them back into this formula here. So the tangent of alpha, that is radical 3. So we have radical 3 plus the tangent of beta is 1. There's our numerator. And then the denominator, 1 minus. Now these two tangents multiplied. So we have square root 3 times 1. So this is square root 3 plus 1 in the numerator and 1 minus the square root 3 in the denominator. So this is the end of the trigonometry. This is our answer. There's a but here. We know from other work in math, whenever we have a radical sign in the denominator, we're going to rationalize that. So coming down here now, we have radical 3 plus 1 over 1 minus square root 3. I just copied our trig answer from here. This is no longer trigonometry. This is algebra now on rationalizing the denominator. So we multiply by the conjugate, which would be 1 plus the square root of 3 over 1 plus the square root of 3. Because remember, any multiplication we need to do in the denominator to clean that up and get rid of the radical sign, we have to do the same multiplication up there in the numerator. So looking at the multiplication, I'm going to do the denominator first because for me that's easy. When we have conjugates and we're multiplying them, this turns out to be 1 times 1, which is 1. Square root 3 times square root 3 is 3. And now we have the minus in between because negative times positive is negative. And then in our FOIL multiplication, the outer and inner terms, they just cancel out because they are the same but opposite signs. That's how, remember, the conjugate works. In the numerator, I'll do this multiplication out just so that it's clear what we're doing. Some of you could do these faster. So just you can put the video on pause or go get a drink or something. Square root 3 times 1, that would be square root 3. So that's our first. For our outer term, square root 3 times square root 3, that's going to be plus 3. Now for our inner, 1 times 1 is 1. And last but not least, for our last terms, 1 times square root 3 is square root 3. So that's doing the FOIL out the long way in the numerator. So now we can clean this up a little bit. Square root 3 plus square root 3. We have 2 square root 3. Notice you do not say 3 and 3. No square root 6 underneath there. Can't touch what's under those radicals. It's 1 and 1 on the outside is equal to the 2. And then 3 plus 1 is 4. And cleaning up the denominator, 1 minus 3 is negative 2. So we've gotten rid of the radical in the denominator, but we're not quite done because when we look at this, we can see we can divide by 2 down here, 2 over here, and 2 over here. So these can all be simplified. This would be 1. This would be negative 1, and this would be 2, dividing everything by that 2. Well, this looks like quite the mess, doesn't it? So over here, we're left with the square root of 3. And then over here, we have plus 2. And in our denominator now, we're left with a negative 1. And we are just about done. The final step would be to get rid of this negative 1. So one way to do it would just to be this. Put the negative 1 out front and then put square root 3 plus 2. Or you could say distribute the negative 1, negative 3 minus 2. Whoops. To show that, because we don't need that 1 in the denominator, but we can't just get rid of the negative sign. So we either put it in front of the whole numerator or distribute it. So in this particular problem, I don't think the trig and the formula was difficult. Probably a lot of you are going to complain that it is this rationalizing process that's the bulk of the work. And similar to what we looked at with the sine and cosine examples, we're also able to use the formula going in the other direction. So we have this here. Tangent of 50, tangent of 20. Without a calculator, we're not able to evaluate this information as it is. So when we look at this, we can see, as I've said before, it looks suspiciously similar to some of the formulas that we looked at before. We have a tangent and a tangent with a minus sign. So if we go back to the sheet, tangent and tangent with a minus sign in the numerator, and then a plus sign in the denominator, that is the formula for the tangent of alpha minus beta. So this is the formula for the tangent of an alpha minus a beta. So we have to figure out what's alpha and what's beta. Alpha is going to be 50 degrees, and then our beta is going to be 20 degrees. So now we look to the formula and we put in our alpha and beta. So we have tangent of 50 degrees minus our 20 degrees. So we're looking at the tangent of 50 minus 20 of 30 degrees. And we know that the tangent of 30 degrees is radical 3 over 3. And that would be our answer.